I thought we would go ahead and start out this lecture with a fun digital equivalent of swarm intelligence, and then we'll get back to the homework and do the homework. The digital equivalent of swarm intelligence is something called cellular automata. And the most famous cellular automata example that came out was Conway's Game of Life. And I wanted to show you the game of life. Again, we are characterized by very simple rules, but those simple rules can manifest themselves into extraordinary patterns and get you some extraordinary emergent results. So I have let's see, I think I have here queued up a very nice YouTube video with over 4 million views of Conway's Game of Life. So let me go ahead and share my screen. Everybody see my screen? Okay, I don't know what happened to everybody. My little view isn't very good. Can you see my screen? Give me a thumbs up if you can. Okay, you can see the Conway's Game of Life. Let me show it to you. And it's pretty well self-explanatory. It's laid out on an infinite grid, and it obeys very simple rules, much like the swarm intelligence, yet you can get very fascinating results. And the fascinating results that you get are many times they have to be engineered in the sense that you have these people that spend a lot of time messing around with the game of life and the simple rules that are associated with the game of life and begin an initialization that allows incredible things to happen. And we'll see this. I want you to notice that the game of life is totally deterministic. It has nothing random in it, yet this determinism still gives rise to very interesting phenomena. So let's go ahead and start this, and I'll maximize it. And I won't use the music. We won't have the music. And we'll see what happens. Okay, a cell can be either alive or dead. And it's determined by its surroundings. So living cells can die, or they can stay on and live. If there's overpopulation, if you have 3 or more neighbors and you're alive, you die. But any dead cell with exactly 3 life neighbors becomes a live cell, as if by reproduction. Okay, let's see what you can do with those 4 simple rules, very simple rules, just like in swarm intelligence. One of them is these little, they're called gliders. And this is very interesting. You have this little pattern here, which is a glider generator. So it goes back and forth with Conway's 4 rules, and it generates these little gliders. And here is interesting also, you have 2 glider generators that launch gliders in 45-degree angles to each other. And when they get together, they annihilate each other. And this is the 2 side by side. We have an endless stream on the right and an annihilation on the left. Here we have a manufacturing plant that these 4 rules literally generate from gliders spaceships. They self-organize into spaceships, and these spaceships go from the left to the right, as you can see them here. I believe this is a simple Turing machine that is actually doing some computation. Lots of stuff going on here. Just remember, just 4 simple rules. And these were engineered by people that like to sit down. They have a lot of free time on their hands, and they generate these incredible results. Yeah, could you guys, if you're not going to talk, could you mute yourselves, please? That last one was called a puffer because it left kind of a trail behind it. Here's another manufacturing ship. There's another annihilation. I don't know, that one kind of looks like fireworks, doesn't it? This one is referred to as an oscillator because it keeps repeating. Lots of the patterns are indeed oscillators, and we see an oscillator here. An oscillator is a periodic replication. A glider, on the other hand, is something that replicates itself, but after the replication, it is displaced once. I'm not sure what this one's supposed to be showing us, but I guess everything is self-annihilating. Here, the entire plane is populated, and then a decimation occurs as a disease spreads. Here's battling spaceships. Here are 2 manufacturers of spaceships from gliders. It looked like some gliders coming by. Again, this is the digital equivalent of swarm intelligence. We simply have rules. They're very simple rules. In the game of life, we have 4 rules. Conway is purported to have sat down with the checkerboard and tried a number of different rules until he got a set of rules which he thought was pretty cool. They could do some interesting things. These look to be oscillators. Here are some gliders. Just very fascinating things. We're just about done. We know we're just about done because we're getting the advertisement for the next for the next YouTube video. Okay, so that's Conway's game of life. Now, this has been generalized by Wolfram. Anybody recognize the name Wolfram? Wolfram is the guy behind Mathematica. He is just an incredible genius in mathematics. If you look at Wolfram Mathematics, he's the one that has on the web this integral solver. He has, well, again, Mathematica. If you use Mathematica, it's a symbolic package which does your operations symbolically as opposed to numerically, like something like MATLAB. And it's just astonishingly good. He wrote a book called A New Type of Science, and what he did is he messed around with automaton of the type that we just saw, and was able to get all sorts of interesting things. He has a book which is about this thick. Now, are there any applications of this sort of thing? Well, yes, it turns out in our department, Keith Schubert is using a model of these automata for rare life. Let's see, what's the word? I'm looking for the word for rare life. When you go down into sulfur caves, there will be life in sulfur caves. and this life will be very, very rudimentary. And many times it has this cellular sort of formation. And he was looking for, down in these sulfur caves, if you look at extreme life, that's the word I'm looking for. He was looking at this extreme life and seeing if he could come up with some automata rules that describe the replication of this extreme life that's found in sulfur caves. Yeah, in fact, Dr. Schubert was on a mission and went down in some of these caves. And the irony is, if you've had Dr. Schubert, anybody had Dr. Schubert for a class? Just an incredibly brilliant man. He was funded by NASA to go down to these sulfur caves. Now, why would NASA fund extreme life? Well, for the simple reason that if there is life on other planets, there's a chance that it will be this extreme life. And so they want a kind of a heads up on, the sort of life forms that they might find on other planets. Another thing this illustrates, there's a number of things that it illustrates. Number one is the halting problem. Many of these patterns that you put up in the game of life and these automata sort of games begin to, and then they go away. It totally annihilates itself. Other forms of life live on forever, as you've seen with the generated gliders and things of that sort. There is something called the ash in the game of life. The ash is something that happens when you just you turn on a bunch of pixels kind of at random and then look at what happens. And then you do bloop and you do something else and you see what happens. Well, it's not very surprising that very rudimentary artifacts occur from the ash. There's never anything complicated like we saw. In order to get something complicated like we saw, it would take a lot of design. It would take a lot of people sitting down, a lot of people with a lot of free time. And there are game of life groups, if you will, that sit down and do this. And it'll take a heck of a lot of time to get some of those incredibly complex patterns that we have seen. And I didn't finish my thought on the other one. If you have some ash, the question is from that initialization, everything is deterministic. You recognize everything is deterministic. There's nothing stochastic in here. There's nothing random. And to just see what happens when you choose things at random, is this going to annihilate itself, or is it going to generate something which never ends? This is reminiscent of the Turing halting problem, where if you ask yourself whether a program will halt or whether it will run forever. And this is the case of the Turing, not the Turing halting problem, but this is the case of the game of life. It's very difficult just to examine the initial layout, the input to the program, the rules of the program, and then decide whether that system will self-annihilate or whether it will go on and it will run forever, if you will. So it's often pointed to as an example of where of the Turing halting problem and something which cannot be solved algorithmically. Maybe it can, but I think that it is an interesting example. So that is the equivalent of the digital swarm, if you will, which is laid out on a grid, and we form some simple Boolean sort of rules and generate these very interesting, fascinating patterns. Any comments or thoughts about this?
I mean, it's really cool how many complex things I can come up with.
Oh, it's amazing. And by the way, Dr. Schubert and his team that went down in these sulfur caves were featured in an issue of National Geographic. I wish I could give you the chapter and verse, but it was really a big deal, some of the things they were doing. Okay. No, yeah, it is. It's fascinating. And again, all of these things are designed. It has to be put together by a creative intellect in order to get these things which are more complex than, say, a simple glider. You have different types of objects. You have, for example, the stationary ones. If you have a little block of 4, that turns out to satisfy all the rules very nice, and it just stays the little block of 4. That's the most simple. Then you have oscillators. These oscillators repeat each other. They go blink, 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 and they just go back and forth. So oscillators are the second most common sort of form. The third is the glider, and the glider is something which can be created from ash if you do enough ash, enough random generalization, because these gliders can come out and begin to do things, the simple gliders. But anything more complex than that, the puffer, the assembly of spaceships from gliders, I find that just fascinating. And somebody had a heck of a lot of time to devote to the development of these things in the game of life. So that being the case, let's switch gears now and go back to the homework. And I'm going to put up the homework. And we can talk about it very quickly before we get into the next topic that we're going to be talking about. Okay, where'd you go? I always lose my little share screen thing. Okay, here we go. Okay, hopefully you can see my spreadsheet here. And these are the homeworks that we had. So let's go through the first one. I wanted you to choose a couple of things. I made some suggestions. You didn't have to do that. You didn't have to choose the sequence of numbers between 1 and 0. But I wanted a plot of this as a function of alpha for the aggregation operator to show it went from the min to the max, and it passes through the geometric mean, it passes through the average, it passes through the harmonic mean, and just remarkably passes all of the different aggregations that we use typically to characterize a list of numbers with one number. So let's do this. We don't have with us who? 1, 2, 3, 4, 5. Somebody is missing. Who is missing? Or maybe we're not. Maybe you're off screen. You are, Matthew. You were the lagger. You were off my screen, but you have been redeemed since I have found you. Okay, we'll start out with Sam is 0. I'm going from my top to the bottom. Sam is 0. Remember your number now. Ming Kun as 2. Innocent is 3. Trevor is 4. Colin, you're 5. And Matthew, you are 6. Okay. 0, 1, 2. No, I can't count.
Dr. Marks, you skipped 1.
Okay. Sam is 1. Ming Kun, I'm sorry, Sam is 0. Ming Kun. I can't count anymore, for Pete's sake. Okay, Sam is 0. Ming Kun is 1. Innocent is 2. Trevor is 3. Colin is 4. And Matthew is 5. There we go. Do y'all remember your numbers? Okay, good. So let's do the first one. We choose a few short sequences of numbers between 0 and 1. And I wanted you to include 0 and 1 because I wanted this plot to go between the minimum and the maximum. So I wanted it to go between 0 and 1 and see what you got. Now I chose just 4. You could have chose 6, 20, ever how many elements you wanted in that vector. But let's see what you did. So I'm going to flip here with my random number generator with my coins here. And I got a tails, heads, tails. So that's a 2, 0, 1, 2. So Innocent, show us what you got. By the way, if you didn't do it, say I didn't do it, and we'll flip again. Innocent, do you have anything for us?
Yes, I do.
Oh, but I probably have to stop sharing, number 1, and I have to give you permission to share the screen. Okay, I think we're okay now. Go ahead, Innocent.
So are you guys seeing, okay, wait. I guess you are seeing it now, right?
Yeah, I can see that. Okay.
Okay, so this is what I got. I did the sequence of them 0, 1, 2, 2, and 1.
Okay, is alpha your horizontal axis?
Yes, that's alpha.
Okay, now it's interesting. I guess it bothers me that it goes so directly to zero and doesn't, and is zero for negative values. That bothers me. Did anybody else get a result that didn't go directly to zero there?
Dr. Mark?
I originally did, but then I included a lot of ones and then it kind of raised it.
Okay, so this is what you saw for the,
Yeah, when I did it, I noticed a very sharp decline to zero over negative values for mine.
okay, so that was characteristic of them all. Okay,
So-
do you have one? Okay, go ahead.
What I notice is that that sharp corner happens when you have when a zero is contained in the set that you're taking the mean, because for alpha equals -1, you
Oh
get
my
the harmonic
goodness.
mean.
You're
which isn't
right. You get
defined
the
on zero.
harmonic mean and you get an infinite, a 1 over infinity sort of component, don't you? So that should be
yeah.
there if you have a zero. Okay. So
if you do a really small, you get a nice S curve.
okay, do you have an example of that, Matthew? Go ahead and stop sharing, Innocent. This is good. I'd never seen this result before, so it's this is good. I've learned something.
Hang on, MATLAB starting.
Okay, waiting for MATLAB to boot. Okay, while this is happening, I wanted to mention that there will be no class regular time on Tuesday, and I wanted to talk about your availability at other times on Tuesday. Would you be available to meet after the scheduled class, say at 5 o'clock? Is there anybody unable to meet then? If you are, what I propose is that next Tuesday and only next Tuesday, I will give the lecture from 5 until, well, plus whatever the class time is. And then I will post it on YouTube. So if you're not available to watch it or to participate live, you'll be able to watch it on YouTube. Okay. So that's next Tuesday, starting at 5.
Dr. Marks, that sounds good. Just a heads up, I won't be able to join until around 5:15.
Okay.
I can watch the first bit on YouTube, so that's fine.
Okay, good, good. I usually mumble for the first 5 minutes anyway. Okay, so here we have a 0.1, 0.2, 0.8, and 1. So we see here that that we do have a nice S-shaped curve, a nice, as it's referred to sometimes, a sigmoid. Okay, and there, oh, so you can change it here in real time. Make the minimum, for example, 0.2, 0.2, see what happens there. Oh, not much happens. Try 0.5, 0.5. Okay. Well, that's kind of more like it. You notice that you do have a zero in there. The geometric mean at zero always has to go through zero. And it never occurred to me before that 1 over 0 would aggregate always to a 1 over 0 infinity that's usually in the denominator, and that goes to 0. So we do have that aggregation. So Innocent's curve was totally correct. Okay, this is great. This is great. As I mentioned, I've never seen this before, and and I've learned something. So that's good for me. Always like learning stuff. Okay, let's go back to the spreadsheet. Show that the Jaeger intersection and union are associative. Okay, let's choose somebody. Okay, let's see who did that. Innocent did it, and I need to write this down. Innocent and Matthew. Okay. Okay, show that the Jaeger intersection and union are associative. We have tails, heads. I don't know what the heck is. This is it's an aluminum coin. Do you know, by the way, there's one coin in the world that floats? Anybody guess what it is? The Japanese yen. It's made of aluminum and it's so thin. Now, aluminum is heavier than water, but it turns out you can make it float on water by just the surface tension if you're very, very careful in putting the Japanese yen into water. Now you know, more trivia from me. Okay, tails, zero. This is you, Sam.
All right. Can everyone see this?
Yes.
Okay. So here I started with the union to show that it's associative. It's given by this. To show it's associative, you just have to show that this is equal to that. So on the left here, I did the left side of the equation, and on the right, I did the right side of the equation. Once you do just a little bit of simplifying, you have to break it up into cases because of the min and, well, there's probably another way to do it, but the way I did it was to break it up into cases.
You did kind of a tree branching here, right?
Right. And so for both cases, it works out that they're equal to each other. So I got that the union was associative. Then the intersection was given by this. This one, I did it top and bottom because I didn't have enough room left to right. So the pseudo left-hand side of the equation would be this first little bit. And then the second part of it would be, oh, wait, no. For this one, I just noted that they were all functionally equivalent. And so it didn't matter if you switched them around because I didn't feel like writing all out again.
Okay, so simply because all of the elements were there and could be interchanged, then it was the
Right.
same. Okay.
Yep. So that was more of an engineering proof than a math one. But
No, I think that is a good solid math proof. I have no problem with that.
well, cool.
Yeah.
That's what I got.
Okay, well, good. Okay, let's go back and look at some more here. Okay, here we go. Now, each one of you had a result. And I wanted to just go through everybody and see what your result was. And we'll start at the bottom with, let's see, Ming Kun. Could you go ahead? Which one was assigned to you?
Hamilton.
Okay, what'd you find out with Hamilton?
Yeah, let me see. Yeah, this is let me see. Yeah, so this is my so for the law of the contradiction, that is x and x bar equals to 0. So so I take the intersection to prove to see it. So after I put into the AB is the original form and A1 minus A to see if this is equal to 0, and finally what I get is here, and suppose A equals to 0.5 and the gamma equals to 1, and finally I can get 0.25, and this is not 0. So
okay, so it doesn't satisfy the law of contradiction.
No.
Okay, just give us the highlights. The law of excluded middle. I think you can say there that it also does not satisfy the law of excluded middle, right?
Yeah.
And you have the math here. Okay, interesting. Okay, go ahead with the intersection.
For the intersection A, and finally what I got is that suppose gamma equals to 1 and actually intersection A equals to A squared. So this now satisfied.
So it doesn't satisfy intersection. I wonder why this got so famous. Does it do anything? Go on to the next page.
Actually, one thing I think maybe interesting is about the association. Actually, finally, what I get is here. Suppose gamma equals to 1. Suppose this one is the general form of the association. But suppose if gamma equals 1, there are some terms can be canceled out. So what we can get is a plus b plus c minus ab minus ac minus bc and plus abc, and this form is actually equals to this. And but when gamma equals to 2, and the association is not satisfied. And the same with the intersection. The intersection is also satisfied when gamma equals to 1.
Oh, so
So-
therefore it matches, you're saying that it matches the boundary conditions.
Yeah, I think when gamma equals to 1 for the association, both of the union and the intersection satisfy.
Okay.
So Dr. Marks, sorry to interrupt. I think the gamma is the parameter. So I think he's saying that when the parameter is at a certain value, it's associative, but when it's not at that value, it's not.
Yeah, and the only
Oh,
thing,
okay. I see. So for different values of gamma, it does work.
yeah.
Okay. Now, this doesn't seem to be very useful. Do you get that feeling in terms of satisfying all the axioms?
Yeah.
Okay. Well, thank you, Ming Kung. That's very interesting. Okay, let's go with, let's see, with, I don't know, Trevor. Which one did you get? I'm wondering if all of these are strikeouts.
So I had the Du Bois and Prod.
Du Bois and Prod, by the way, were just incredibly prolific people in the fuzzy area, and they always came to the conferences together. I think they lived together. They were good buddies, and they did a lot of very interesting work. Okay, what do we got?
So just taking the union and the intersection of Du Bois and Prod. I just did it by plugging in arbitrary values for A, B, and the parameter alpha.
Oh, that's good enough.
And-
That's good enough to show that it doesn't work, right?
Yep.
Okay. Okay, so that doesn't work. Okay, anything else? Anything with the associativity? Or-
Yeah, let me. So with both the or with the idempotents, we notice that for, I believe it's the intersection, it's only idempotent when alpha is less than or equal to A.
Really?
Yes. Because otherwise, obviously, you're going to have this A squared value on top because you're just plugging it in with itself. And so on the bottom, you have a maximum function. And
I
so
see.
if alpha is greater than A, then the, I guess, division won't equal out as compared to A squared over A.
That's fascinating. Okay, associativity.
And so for associativity, it did look messy.
Yes.
Just from the
No,
get-go.
it not only looks messy, it is messy.
Yeah. So I did the same exact thing as I did in earlier ones, just assign the same arbitrary values. And so for this one, I started with A union B and got 0.6, and then set C to an arbitrary value and determined that with those arbitrary values is 0.9, and then tried it with B and C first, and then did it with A afterwards, and I ended up with 0.9 as well. So the union is associative.
Okay, well, you haven't proved it. You've just showed a incident where it's associative, right?
Yes.
Okay. Now that is an engineer's proof. Okay. Okay. So we're not totally convinced, but at least it works here. Okay, go ahead.
So I went with another engineer's proof over here for the intersection. Using the same exact values, it did come out to be associative with the intersection.
Now, did you check it? You said before it depended whether A was greater or less than alpha. Did you check that out here too? It seems that that should be something you should check out for these different cases.
So I didn't check it with the associativity. I had noticed that that was a just with the idempotence. So it might come up as different as alpha goes from a higher value compared to either A, B, or C.
Okay. Okay. Fascinating. Okay. Innocent, what'd you get? You're muted, Innocent.
So I worked on the hemisphere. There you go. Okay. So I worked on the same problem as Min Kun because I was to like pick a choice on the one to work with.
Okay, just walk us through the conclusions, your conclusions.
I had the same result as him, but when it comes to the associativity, I didn't notice what he did because I only worked with lambda equal to 1.
Okay, so it works for a given value of lambda, but not in general, right?
Yeah, I didn't notice that because I only worked with lambda equal to 1. I didn't try other values of lambda. So it worked for when lambda was equal to 1.
Okay, but it failed for the other values.
Yeah. Yeah.
Okay. Okay, was this true for the associativity and the other things?
Sorry?
The law of contradiction, excluded middle, associativity, the things I asked you to look at.
Yeah, all those ones, yeah. I got the same result as Min Kun, like for the law of contradiction. It wasn't equal to 1, it was like
Okay,
0.25.
so it doesn't work there. And
Yeah,
the
it doesn't
law,
work here.
okay, it's the law of contradiction, the law of excluded middle, neither one of them works then. Okay.
Yeah.
Okay, is the union associative?
So I worked with lambda equal to 1, or sorry, gamma equal to 1. So it worked for
I don't
gamma
think,
equal
okay, you're saying gamma. I kept hearing lambda, but that's gamma. Okay, go ahead.
it worked for gamma equal to 1 right here. So it is an associative right here. When I search that, I got an A plus B minus AB.
Okay.
So this is like the union and the union. So the left hand side, when you did the union of AB, the union of AB together with the union of AB and C is equal to the union of A with the union of B and C.
Okay, interesting.
Yeah.
Okay, well, thank you very much, Innocent. Let's go on to Colin.
All right, let me share my screen. All right, so I did the Dombey fuzzy logic, which is given by this last cell in the table.
Yes.
Just a little bit bigger. So it doesn't satisfy the law of excluded middle or law of contradiction. Because this would result in LaTeX that would look kind of like vomit on the page, I did a little bit of simplification.
Okay.
So I just looked at these quantities in brackets first and denoted it as B sub A, and found that when you fixed lambda equal to 1, they coincided, which here's sort of the proof of that. I guess that's sort of our intermediate lemma. And then using that lemma, we can just plug in values as just as a simple counterexample. Alpha equals 1/4. We get the quantity in brackets is 3 1/3, which is 4/3, which is not quite equal to 1. So it's close, but not exact.
Okay, how can we get 4/3? How can we get something? Oh, I see. Okay, that's an intermediate result. That's not the final result.
Right.
Okay, yes, I see. I see.
So yeah, the final result was 4/7. So it was greater than a half, but not quite equal to 1.
Okay, and we also okay. Let's talk about about the union of A with A in the intersection. So you found it didn't work there, huh?
No, it's not idempotent, unfortunately.
Okay.
The reason being is that when you plug it in, you end up with this 2 to the negative 1 over lambda.
Yeah.
And that in the denominator sort of accumulates over time. So it's not idempotent,
Okay.
both the union and the intersection. But at least the operations are associative.
Oh, okay. Well,
So,
a little island of happiness here. Good.
yeah. So if you plug it in, after a little bit of reworking, you sort of see that these sort of the quantities in brackets sort of just get added together in a series summation, all raised to the power negative lambda in the case of the union, and in the case of the intersection, it's that same summation.
Yeah. So it
all of them.
doesn't matter how you shuffle them. It's going to be the same. Good.
Right.
Isn't that interesting? Okay, go ahead. Oh, okay. I guess that's it. That's it.
Yep.
Okay, great. Let's see. Who do we have left? Sam, I think you're left.
Yes, I still have to go. Okay, I did the Schweitzer and Sklar. It starts here. So I started with the law of excluded middles here, and I proved that with a counterexample that it's not equal to 0. And then I used let's see. What did I do here? Okay, so yeah, this would be the law of contradiction. Wait, did I start it on the previous page? Yes, okay, sorry. I started with contradiction here, and I tested that with a counterexample, found out that it was not the case. And then excluded middles, got a counterexample, proved that that was not the case.
Okay, so just one counterexample goofs it up. Okay.
Right. Let's see. So B for the intersection, this would be for idempotence of the intersection. This is not equal to A, so it's not the case. And then for union, I also got that it was not idempotent because it's not equal to its associativity here. I found out that the union here is not associative because we have these two terms are to the negative 1 power and the other term is not. And I for all of these things, I ran through MATLAB with A, B, and C, all of them going between 0 and 1 with all the combinations to see if they were associative, and they were not. Here for associativity of the intersection, I found out that they were. Here I broke it up into the same kind of logic cases that I did earlier, and they all matched up. And then I tested all the possible combinations of A, B, and C between 0 and 1. Well, not all of them, but with a step size of 0.01.
Okay, so the intersection was associative, you're saying? Yes.
But the union was not. The union, funny story, is very misbehaved. And I will get to that in just a second. Next up, I went to idempotence. And while I was doing idempotence, I noticed that the intersection is not even bounded between 0 and 1. The union is
Really?
not even bounded. And so let me bring up the equation for it, because I know what you're thinking, maybe you misread it.
Yeah, I wonder if that's a misprint in clear and full.
Yeah, I think it is. So here, this is the fuzzy union for Schweitzer and Sklar. If this to the 1 over p power was a negative, it would be bounded between 0 and 1, but it is not. So for values of 0.5 and 0.5 and a p-value of 2, you would get, what would you get? You'd get 0.5 to the negative 2, so that's 4. Then plus 0.5 to the negative 2, which is 8, minus 1 is 7 to the 1/2 power, so you get the square root of 7. And not a value between 0 and 1.
I see. So we probably have a typo there.
Right. So I think if this was a negative, it might behave better. I didn't do all the math again for the correction because I didn't feel like that was necessary. But yes, I found out that the union was misprinted. let's see, I did idempotence. I did a counterexample in both cases, found out that neither was idempotent.
Okay, very good. Does that make everybody? I think we went through everybody, didn't we?
I don't think.
Oh, Matthew. Okay, Matthew, are you, if I left you out?
I answered an earlier question, but not this one.
Okay, okay. It's just my familiarity with your face that made me pass you over. So we don't want to do that again. Please go ahead and share your result.
Okay, so I've been pretty busy in the brick and haven't had time to completely type it up. But I'm working on Frank, which is this nasty logarithm. Let's see. I don't know if I can show my work on paper, but if you work it down a little bit, and then I noted as others did earlier that it suffices if you just pick an A in your interval and then an F in the one that it points out, and show that the law of excluded middle and the law of contradiction don't work. You can do that. So then here I graphed the union and intersection of A equals 0.5. I graphed that against F, defined in the domain. And it's pretty clear from this that, for example, this is the union, and this does not equal 1. And then this is the intersection, and that does not equal 0.
Okay. So you got part of this. This is very interesting. Okay.
I solved the other two, but they're on paper.
Okay,
So,
do you remember your conclusion?
Oh, so let's see. It was associativity.
Maybe you don't remember, and that's okay. We'll take a look at it in the homework that you submit.
It is idempotent.
It is idempotent.
Yeah. Actually, no, I'm working on idempotent.
Okay, we don't know if it's
it
idempotent.
is associative though.
It is associative. Okay.
Mm-hmm.
Okay, thank you, Matthew. So what does anybody have a conclusion for all of this list of ands and ors, fuzzy ands and ors that are given clear and Folger? It's kind of, yeah, it does seem a little unnecessary. And why do you think that these were proposed? Probably to get the people who proposed them a publication, another line on their CV. And I'm sure that they have a justification, but I think in each case we'd have to go specifically to the paper where these were introduced to find out the reason that these people introduced them. It seems that none of them satisfied the law of non-contradiction and the law of excluded middle. And that would be fun because I didn't know when I made this assignment, I didn't know that if some of those were able to satisfy non-contradiction, the law of excluded middle, but clearly they don't. And that's weird. I wonder if any fuzzy union and intersection follows that result, or maybe we're just stuck with it in the Boolean case. Maybe in the fuzzy case, it just doesn't happen. I don't know. So very good. Thank you guys. That was very, very interesting. And yeah, my conclusion is this is a much ado about nothing, to quote a Shakespeare play. There is very little I can see in terms of use of these. And because of this, the min-max logic is used a lot in fuzzy logic, as is sum product logic. We didn't go through sum product logic, but certainly it's commutative, and it is not associative. It is not idempotent either, but it's used a lot. And the fact that the sum product is something that can be used is so simple. There's none of these logarithms. There's nothing raising nothing to the power. It's just adding and multiplying and making sure that the summation is not greater than 1. That's the sum product. And this shows you again the incredible power of fuzzy logic, that you can use all of these different sort of garbage sort of relationships and still come out with a decent fuzzy system in terms of using these different aggregations. I'm not sure about the ones that we went through today, but I'm sure that the sum product and the min max are the ones that are used predominantly today. Any other thoughts or questions? Okay, if not, I want to go into I want to avoid being what I referred to as a keyboard engineer. A keyboard engineer is one where they're confronted with a problem and they immediately go to the keyboard to can software in order to solve their problem. We see this a lot, especially in neural networks and deep convolutional neural networks and some of these other things, without an understanding of some of the deep concerns of what is going on here, the theory. I'm not talking about the specifics of the mathematics behind the training, but more of the philosophy of what is going on here, what is necessary. I have a friend, Jim Bezdek, who does a lot of consulting where he's given big globs of data and he's told to do something with it. And the first thing that he does, in his words, is he kind of spreads it out on the floor, he wets it down with water, and then does a belly flop in the data and becomes familiar with it. In other words, he develops a domain expertise. He develops a friendliness with the data that he's analyzing. Then and only then does he begin to apply algorithms. So what is going on with this sort of problem and this sort of philosophy? And I want to develop, hopefully, a philosophy associated with this. So I'm going to share my screen. And this is kind of an introduction to search. Do you see my PowerPoint? Okay, you can see my PowerPoint. This is kind of an introduction to search. I wanted to talk about search and what it means to do a search, to optimize. As I mentioned, design itself is typically an iterative process. We had the Formula 409 and the WD-40 as examples of iterative search. And you know yourself, if you go to the laboratory and you try to define or design a circuit, then your first design might not be good. You might have to tweak it a little bit in order to get it to work, in order to get it into the area of acceptance. So let's talk about search, and we'll also find out that training, neural network training and AI training is a search itself. So search is something which is applied to the training of AI. First of all, we have to rid ourselves of presuppositions and talk about the fact that knowing nothing means knowing nothing. And if you know nothing about the search that you're doing, that means that you know nothing about the search that you're doing. A lot of people come in and they make assumptions about the search, and those assumptions are not as deep as they possibly can be. Let me challenge you with the following exercise in knowing nothing, and that is with the creation of the universe. Have I gone through this before, the idea of knowing nothing? Okay, here is the account from the Big Bang, from classical Hubble law, if you will. You all know that Hubble figured out that the universe was expanding, ever expanding. And if you go backwards in time, that means it came from a single point. A guy named Fred Hoyle came along and he made fun of the idea that the universe had a beginning. Most people thought that the universe was infinitely old or was cycling or something. It turned out that actually Newton figured out that the universe had to be infinite in size, and infinity exists nowhere in reality. It either had to be infinite in size or it had to be expanding. And the way he did this was very simple. He says, if the universe was finite in size because of the gravity that he had discovered, what would happen if the universe were finite in size and time progressed for a long time? What would happen? All of the masses would attract each other, wouldn't they? And the universe would have gotten together in a big blob. So even Newton recognized that the universe either must be infinite or must be doing something. It must be expanding in order for it to not have collapsed totally on itself. So let's talk about the Big Bang. Before the Big Bang, there was nothing. And this is both, by the way, the classical physics approach. I think it's also very biblical. So before the Big Bang, there was nothing. Now, I don't know about you, but when I look at the Big Bang, I visualize it as a big empty space. And then all of a sudden, no, you can't do that, because before the Big Bang, there was nothing. And a big empty space is something. Before the Big Bang, space did not exist, because nothing existed before the Big Bang. Okay, so if we accept that premise and we go to the Big Bang and we say, okay, try to get space out of my mind. And then you say, okay, there's no space, but then all of a sudden, no, you can't say all of a sudden either. You know why? Because all of a sudden assumes that there was time. And time did not exist before the Big Bang. I first read this and I was kind of surprised in Stephen Hawking's A Brief History of Time, and looked into it more deeply. And yeah, it's true. There is the idea that time did not exist before the Big Bang. So I don't know about you, I cannot visualize a world without time or space, but that is truly nothing, and nothing means nothing. And we have these presuppositions that kind of sneak in about, for example, the Big Bang, that there was a space, and then all of a sudden, no, you can't do that. You have to really recognize that nothing means nothing. And we're going to apply nothing not to cosmology, but to the process of search. And we're going to look at the case where you know nothing about the search that you're generating. And knowing nothing about the search is sometimes difficult to place yourself mentally in, because again, knowing nothing means knowing nothing. And many times we have these little biases that kind of sneak in. We're numbed by familiarity, and these things sneak in. So we have to be very careful about it. So with that, let's look at a very rudimentary example of searching for a good pancake. Now, we're in the kitchen. We know we have some pancake batter. We know nothing about the pancakes that we're going to cook, nothing at all about them. But the only thing that we know is we have to figure out how much to cook the pancake on side one, and then how much to cook the pancake on side two, how long to cook the pancake. Now we're going to divide this up into 15-second intervals for 10, what's 10, 15 seconds? That's a minute and a half. No, let's see, 2 minutes and a half, 2.5 minutes. So 1 would correspond to 15 seconds, 2 would correspond to 30 seconds, 3 would correspond to 45 seconds, a minute, etc. So this is our search space. So we're going to have 10 possibilities for putting the pancake on side one and then the pancake on side two. And we're going to assess this by a taster at the end. We'll call it Bob the Taster, and he gives a fuzzy measure of how good the pancake tastes, say on a scale of 1 to 10. So how many, if we want to figure out all of the different possible outcomes of the pancakes, you can see here that we're going to have to fry 100 pancakes, aren't we, in order to totally exhaust that space if we know nothing about the culinary arts. This gives rise to the idea of a fitness landscape. The fitness landscape is shown on the right, and it covers the search space, and every point on this surface has a fitness associated with it. And our job is to find an acceptable pancake. Now, there's a couple of ways we could do it. If you are an aficionado, you say, I want to find the best tasting pancake that I can possibly get. If you are an engineer, you say, look, I may be searching for the best pancake is going to take too much time. So I want to search for a pancake that has a taste that is ranked from either 9 or 10. In other words, that's your design criterion. And usually a design criterion is not to maximize the performance, but to get the performance within a range that is acceptable in accordance to a previously established standard. The military is especially good at this. They have mil specs, military specifications. They have it for everything from jet engines down to toilet paper. And they tell exactly what the design has to meet in order for the military to buy these things. So you can see here that out of all of the sides, that at least for this, that there are 4 possibilities. Now, the problem with this, of course, is before you do the search, you have no idea what the landscape is. You have no idea what the landscape is at all. So what you might do is perform an experiment. And so here we have cooked 4 different pancakes. You can see each one corresponding to a different time on each of the sides. And each one then gives a different point on the fitness landscapes. Now, what does this tell you about the next recipe that you should apply? Well, you can say, let's go close to this top pancake up here on the upper right, and let's cook something kind of around that, because that looks to be pretty big. But notice you're assuming you know something. You're assuming that you know that that fitness landscape is smooth. And if you know nothing about the search that you're doing, if you don't know that it's smooth, you have no idea where to go next. So any point is as good as any other point if you know nothing. And again, it's getting back to knowing nothing. We don't know that the surface is a smooth surface. What happens if you have 3 ingredients? We're going to have not only cooking on side 1 and side 2, but we're going to have the heat setting on the oven. We're going to have 10 different settings for the heat. So setting 1 is low, medium, and a little bit higher. And we're going to have 3 parameters now that we have to optimize. Each one has 10, there's 10 tessellations. There's 10 possibilities for each side. You'll notice now that in order to cook all of the pancakes with only 3 variables, each one with 10 possibilities, it would require 1,000 operations. And notice every time that you add a new ingredient, you're going to multiply the number of recipes that you have by a factor of 10. This is referred to as a curse of dimensionality. You better be very careful in choosing the parameters that you test, especially if you know nothing, okay? And again, we're assuming at this point we know nothing. And here is something very interesting. If we had 100 recipes per second that we could bake, it would take 1/3 of a year if we had 9 ingredients. Say not only the heating on side 1 and side 2 of the heater setting, but for example, the number of cups of pancake mix, the number of cups of milk, the number of slabs of butter, the number of pinches of salt, etc., all the way up to 9. And each one of these 9 had 10 different possibilities. In that case, we would have not 10 cubed, we have 10 to the 9th. 10 to the 9th is 1 billion. So we would have 1 billion possible recipes if we had 9 parameters. So it would take 0.32 years, it turns out, if we did 100 recipes per second. That's a lot of recipes. And you'll notice every time that we add an ingredient to our pancake mix, if we wanted to search them all, we would multiply by 10. So you get up to 22 ingredients, and you see that would be, oh gosh, what do we have? 3.1 trillion different possible recipes. So you can see that the number of possibilities grows incredibly. And we are unable to look at all of these possibilities. It's just not possible. Therefore, we have to apply some domain expertise in order to get a good result without doing exhaustive search, without any knowledge. One of the ways to do this is through a random walk. If I just generated pancake recipes as random, this would be like a random walk. And there is a random versus assisted search. And what is an assisted search? That is the application of domain expertise to let you zero in on the solution with your expertise better than somebody that has no expertise. Here's an example. You know what? I'm going to have to stop sharing my screen, and I'm going to have to reshare it with reshare it here. Whoops. I stopped the recording and started the recording again. Bummer. Share screen, okay. Okay, with this, I'm going to play you a clip. This is an example of a blind search involving a Rubik's Cube from the movie UHF. So let's see if we play it and you can hear it.
Nope. Is this it? Nope. Is this it? Nope. Is this it?
No, George,
Okay. I hope everybody saw that. To me, that's hilarious. That is really, truly a blind search because you have a sighted guy next to a blind guy sitting on a bench, and the guy gives the Rubik Cube a twist and said, "Is this it?" The guy says, "Nope." "Is this it?" "Nope." That is truly what a blind search is all about. So that's an example of a blind search. And you can see without any domain expertise, that search is going to take one heck of a long time. That's generally true for a blind search. We can look at this. Let's see what time it is. Okay, I guess we can make it through this. We can look at this for the monkey and the typewriter. And you're familiar with the idea of the monkey and the typewriter. But we can apply, we can apply 27 keys for the monkey and the typewriter. That's the 26 letters of the alphabet plus the space. And we want to figure out what that monkey can type. There is a great skit by, let's see, who is it? Bob Newhart, where he is one of the supervisors at these monkey typewriters. And he's walking around and saying, "Oh, Chimpo, let's see what you have." "Okay, nah, this is not good." So he goes to another monkey and he looks at that monkey in a typewriter and he says, "Okay, let's see, Frank, what do you got? Let's see, to be or not to be." That is the phlebiscimart. And so the funny part is that if these monkeys at the typewriter ever type anything which is meaningful, they have to type everything which is close to meaningful at the same time. So we're going to apply this, and we are going to apply this to the monkeys at the typewriter and assume that the monkeys have no idea what they are going to choose. By the way, this idea of randomness is equated with the idea of maximum entropy. The same thing in thermodynamics. It's total randomness. And Jacob Bernoulli in 1713, as you can see in the bottom here, wrote this paper, which he said, if you know nothing about what is going on in a search, the best conclusion is to assume that everything is equally probable. Again, equally probable is the same thing as being in maximum entropy. Now, if you know nothing, won't computers eventually catch up? What about Moore's law? Let's assume that Moore's law says that the computer today searches for a target of B is equal to 10,000 bits a year. In other words, you have a super duper computer and it searches through an exhaustive target and it takes it 10,000 bits in order to generate the solution. You give it one more year and you double the computing speed. How many bits do you think it can go through? Anybody make a guess? Do you understand the question? It takes 1 year to plow through, what did I say, 10,000 bits in order to search through 10,000 bits. You double the speed of the computer. How many bits can you do if you double the speed? I think Colin had it. One more. If you double the speed of the computer, you can only get 10,001 bits. So therefore, computer power isn't going to save you. If you double the speed, the faster computer searches for a target of B plus 1, 10,001 bits. Because here's what you have to do. You have to check the 10,000 bits. That'll take you half a year. And that 10,000 bits with the new bit set to 0. And then you have to search those 10,000 bits with the new bit set to 1. And so every time you double it, you only add a single bit in a year. Let's see, I'll play. Okay, I think we'll actually stop here. We'll stop it with impossible. Okay, so is there any questions? We're going through this. Let me give you a anticipation. What about quantum computing? Isn't this going to help? I mean, Moore's law isn't helping. What happens with something called what is it? Is it called Grover's law? I get the two confused.
Grover search?
Yeah, Grover search, which is a way in quantum computing of increasing the speed. What'll happen there? Is that going to help the 10,000 bit? Well, it turns out Grover search basically reduces the search time by a square root. And so instead of 10,000, you'll do 100. Well, that's pretty good. That's pretty good. But if you get up into the billions and trillions and quadrillions, the square root of that is still a large insurmountable number. So it doesn't look like Grover's law, if we ever achieve it in quantum computing, it hasn't been achieved as of yet to any significant degree that I'm aware of, that isn't going to help either. So Moore's law and Grover doesn't help. And so we are stuck with the idea that we have this enormous search space that can happen very, very quickly, as we saw in terms of the cooking of the pancakes. And we can't do it exhaustively. Therefore, we have to apply our experience and our domain expertise in search. And this is something that I see lacking in people that I work with that are, if you will, keyboard engineers, in the sense that they simply go to the software and they think that the software, the deep neural network, is going to generate the result. What they need to do is they need to become friends with the problem and see what domain expertise they can bring into the problem. We're seeing this more and more happening more and more, for example, at Kaggle. Kaggle uses this software, which is available to everybody, such as TensorFlow and PyTorch, and we have all of this great software is available. Instead of throwing the problem at it, we see people in these contests now coming out and saying, what we need to do is we need to do some pre-processing. We need to apply our domain expertise to this problem in order to pre-process the data before we present it in the neural network in order to get the best result out of the neural network. They apply their domain expertise to the design problem. And this is fundamental in any artificial intelligence, in any optimization sort of algorithm. And we'll look more deeply into that next time. Any questions? Okay, go ahead. I'm sorry.
So what happens if tomorrow morning we wake up and somebody submitted a proof that shows P equals NP?
Well, I don't think that'll happen. So if that happens, we'll deal with it when it happens, Colin. You know, it's like saying, what if somebody comes to the patent office with a really good perpetual motion machine? You know, I think it's in that probability. It's about the probability of somebody getting hit by lightning while they're juggling. It's just, you know, it isn't there. It has been an open problem for so long, and it's a complex open problem. We see simple open problems like the Goldbach conjecture and the Collatz conjecture, which still have to be solved. But the P versus NP sort of problem, there have been people that have poked at it, but nobody has solved it. And I doubt that it might not be solvable. You know, it might be one of those things that is true. And this is what Gregory Chaitin says. He says there's things in mathematics that are true because it's true, and totally escapes the realm of proof. And he says that maybe things like the Collatz conjecture and the Goldbach conjecture are things which are true, but they're just true because they're true. They're, if you will, an axiom in themselves. And it could be, and I've heard this speculated, that P versus NP is just one of these axioms, you know, that the difference, the fact that they're different, is true because it's true, and is something which is never going to be solved. So again, we get into philosophy here, and we don't want to get too deep in philosophy. Any other comments? Okay, I would remind you next time we will meet around 5 and videotape it. And thank you very much. So until next time, be of good cheer. Bye-bye.
Dr. Marks, I have a quick
Yes.
question for you if you want to stay on.
Okay.